Here are the top 10 Desmos features that can deepen your understanding of math. Whether you're graphing functions, exploring limits, analyzing data, or calculating probabilities, Desmos lets you visualize concepts in a way that equations alone can't. Let's dive in and see how these tools help me teach math and will also help you truly understand math. Must-know number 1 is the basics of using the graphing calculator in Desmos. So let's start by going to desmos.com, and then in the list of math tools, let's choose the graphing calculator. And in this graphing calculator, I want to show you in this section how we can graph functions, label them, evaluate points, and even solve equations by finding intersections. So let me start actually by going into the graph settings, this wrench that's in the top right, and I'm going to make everything a little bit bigger so it's easier for you to see by clicking this bigger A. And I'd also like to get rid of these minor grid lines as well. And now what I'm going to do is start by graphing a quadratic function. I'm going to graph the quadratic y equals x squared minus 4x plus 3. And now to get this 2 as the exponent on the x, I can use the button on my keyboard that looks like this. Or I can pop open the keyboard in the bottom left of the screen here and use this a squared button to write an exponent of 2. And in fact, anytime you're trying to write a math symbol, if you can't figure out how to use your keyboard, you can pop open this keyboard and find the symbol. And you can even explore the different functions here that you can make use of in Desmos. And now what I want to do, instead of writing y equals this quadratic, I'm going to change it to function notation. I'm going to write f of x equals this quadratic. And now Desmos will recognize this as a named function, so I can easily reference it. For example, if I wanted to know the y value of this function, when x is 4, I could just type f at 4. And notice Desmos tells me that when x is 4, y is 3. And if I click on this quadratic function, anywhere I click, it'll tell me the x and y coordinates of the point that I'm clicking on the function. So when x is 4, I should see that there's a y coordinate of 3. And there it is right there. And also because this function is now named, if I wanted to graph its derivative, that wouldn't be a problem either. I could just write f prime of x, and there's the graph of its derivative. And I could also find the value of this derivative. Let's say I typed f prime at 2. It tells me that the value of the derivative when x is 2 is 0. And now let me show you how we can have Desmos plot any point we want by typing an ordered xy pair. For example, I could type the ordered pair 5, -1, and you'll see that Desmos plots that point down here at 5, -1. Or I could have Desmos plot a point on my quadratic function by typing the ordered pair x f of x for any x value that I want. For example, I could type 2 f at 2 as an ordered pair, and Desmos will plot that point on my function at an x value of 2. And I see it's down here at the vertex, the point 2, -1. And also notice if I click this label option underneath the point, it defaults to labeling it with its x and y coordinates. And the colors and sizes of these points and our function can be adjusted by clicking this settings button, this gear up here in the top of the equation editor. Then by clicking any of the circles beside my function or either of the 2 points, I'll choose that vertex point to f at 2. I could change the size of the point. Right now it's set at a thickness of 8. I could change it to 15 to make it bigger. And I could change the size of its label. Right now the font is at size 1. I could double it, making it size 2 if I wanted to. And that other point, 5, -1, something I could do at that point, I could actually click this drag option, and that allows me to take this point and move it anywhere I want, which is a useful tool if I want to use it as a label for another point. That point 2, -1 is the vertex. So for this red point, I'll drag it right underneath that 2, -1 label, and then I'll add a custom label to it by clicking label, and then writing on this line, I'll write vertex. And then I could hide the point itself by clicking this red circle beside the point, so I now only see that label vertex, which I might want to make bigger by clicking this gear, clicking the circle beside the point, and making the font size, I'll double it. And let me make it the same color as the point. So now I can see that this can be used as a label for that point 2, -1. So that's one way we can manually add points to our function, but there's another option. By clicking this settings gear again, notice beside our quadratic function, there's this create table button. If I click that, it's going to create a table of values for this function, for x values between -2 and 2 by default, but I could add more or less if I wanted to just by adding x values, and it'll calculate the y values using my f of x equation. And then it plots all the points on my function that are in this table. Let me change the color of them so you can see them more clearly. I'll make them purple, and I'll make them a bit bigger. So all those purple points are from this table of values. And now let me actually graph another function on this grid. I'll give it a different name. I'll call it g of x, and I'll make it a linear function, a half x plus 1. Graphing two functions is a great way to see when they're equal to each other. So if you had an equation that had the quadratic set equal to the linear function, you could look on the graph, see where they intersect, and I see they intersect at x values of a half and 4, so those would be the x values that make the equation true, which hopefully demonstrates the power of Desmos for solving equations graphically. And now let me clear these functions and show you one more thing. I'm going to graph a trig function this time, and whenever graphing trig functions, you want to open the graph settings and choose whether you want to be graphing it in radians or degrees. I'm going to use degrees this time, and I'm going to show you the graph of f of x equals sine of x over 2. Notice I'm not able to see all of the properties of this function well with the default scale for the x and y axes. You can try adjusting the scale of this function by clicking these plus and minus zoom in and zoom out buttons. You could try zooming in or zooming out or moving around on the screen by clicking and dragging. But a better way to adjust the scale is to click the graph settings, which is the wrench in the top right here, and then you can manually choose the limits for the x and y axes. Since the period of this function is 720 degrees, I want to be able to visualize at least 2 cycles of this function, so I'm going to make the limits for this x-axis to be between -1000 and 1000. And I'll also change the step, which is the increment at which each unit goes up by. I'm going to change it to 180, so the segments of the cycles are easier to identify. And now looking at this graph, I can more clearly see the properties of this periodic function. Must know number 2, restrictions on the domain of a function. Continuing to look at this exact same sine function, by default, this function will extend infinitely in both directions. I could keep scrolling forever to the right or forever to the left, and this function is just going to continue forever. But what if I only want to see one cycle of this sine wave? To do that, I can restrict the domain by beside the function in my equation editor, in curly brackets, I can state the interval of x values that I want to be displayed. So if I only want one cycle of this function, I can say I only want the x values between 0 and 720 to be displayed. Or maybe instead of just having this one cycle displayed, maybe you wanted one cycle just highlighted. So what you could have done, instead of restricting the domain of that function, we could have written another sine function, so y equals sine of x over 2 again, and then restricted the domain of that one. So in curly brackets, writing x has to be between 0 and 720. And now notice that one cycle of this function is highlighted in purple. And if you ever wanted to hide a graph, just click the button beside its equation, and it makes the graph disappear, or click it again, it brings it back. And now let me get rid of both of these trig functions, because I want to show you how restricting domains can also be useful for graphing piecewise functions. So let me reset my scale. By clicking this house button, it brings me back to the defaults, but I'll have to go into the graph settings to change the step back to its default, which was 2. I'll actually make the step go by 1 for the x and y axis. So if I want to make a piecewise function, which is just a function made up of different functions over different parts of its domain, what I can do is inside curly brackets, I can write condition 1, colon, my first expression, comma, condition 2, colon, my second expression, comma, etc. So if I have a piecewise function, let's call it f of x, what I can do is inside curly brackets, state over what parts of its domain is it equal to what type of function. So I'll say when x is less than or equal to 0, colon, I want it to look like the function x plus 2. But then when x is greater than 0, I want it to look like the square root function, negative root x. And I can find the square root symbol by popping open the keyboard, and there it is right there, square root x. And let's make this function a different color by clicking the settings gear in the top and changing the black color. Let's change it to red. And maybe let's make this function even a bit thicker. I'll change its thickness from 2.5 to 4. Must know number 3, sliders. Now let's talk about one of the most powerful features in Desmos, sliders. Sliders allow us to dynamically change values in our functions, making it easy to explore transformations and different patterns. We can add a slider for a variable just by typing any variable other than x and y and setting it equal to any constant. So for example, I could type a equals 1, and that's going to set a slider for the variable a. A can take on by default any value between negative 10 and 10, and notice that it goes up by an increment of 0.1. I could change the range that a could take on. If I want it to be from negative 20 to 20, I can just type that in here. And if I wanted the step to be by a whole number 1, I could type that as well. But I think I'll put it back to its defaults for now. And now what I could do is I could add a point that will trace along this piecewise function by making the coordinates of the point based on the variable that has the slider. So I could add the point a, f of a, and I'll have it be labeled with its coordinates. And let me change the settings to make this point a little bit bigger. I'll make its thickness 12, and I'll make its label a bit bigger as well. And now see, as I change the value of a, you'll see that point dynamically move on the graph of this piecewise function, and it shows the value of that piecewise function at each point that I scroll through here. This tool with a piecewise function would be great for teaching limits. If I added a vertical line that goes through x equals a, and a horizontal line that goes through y equals f of a, and then restricted their domains and ranges so they just connect to the x and y axes, I can now easily demonstrate the limit of this function as x approaches 0 from both the left and the right. As x approaches 0 from the left, I see that the y value is approaching 2. And as x approaches 0 from the right side of 0, I see the y value is approaching 0. And now let me clear all of this and show you how we can use sliders to demonstrate transformations of functions. Let me write the vertex form equation of a quadratic. So f of x equals a times x minus h squared plus k. Notice Desmos offers me the option to make sliders for those parameters a, h, and k. So I'll click all, and it'll add sliders for all of them. Let me set h and k back to 0. And there we just have the normal quadratic y equals x squared. Let me change the color of it. And now I can play around with these sliders for a, h, and k to see what type of transformations they do to this x squared function. I can see that the a value does vertical stretches and compressions and can also do a vertical reflection. And the h value shifts it right and left, and the k value shifts it up and down. And if you wanted to, you could also have the slider move automatically just by clicking this play button beside any of the variables. And being able to dynamically change the value of variables using sliders has also been fundamental to me being able to explain key concepts in calculus, like for Newton's quotient, showing that the slope of the tangent line at a point is equal to the limit of the secant slopes as the change in x between the points approaches 0. Or that an indefinite integral, which gives the area under a curve, is just equal to the limit of a Riemann sum as the number of rectangles being used to fill the area under the curve approaches infinity. Or even just using it as a tool to show the slope of a tangent line at any point along a function. Must know number 4, shading and inequalities. To graph an inequality, simply use an inequality symbol instead of an equal sign. So for example, notice when graphing y is greater than x plus 2, it shades the region above the line y equals x plus 2 because all of the points in that region satisfy the inequality. Let me actually plot a point in that region, and let me actually make it movable by clicking this settings gear, clicking on that point, and I'll toggle on drag. And I'll also make the label a bit bigger. Notice any of the points in this shaded region, any point in that region, satisfy the original inequality, right? A y value of 2 is greater than the x value of negative 4 plus 2. And another thing to notice is that Desmos makes the boundary line dashed. But if I were to change the inequality, instead of just greater than x plus 2, if I made it greater than or equal to x plus 2 by typing an equal sign here, it changes it to a solid line, showing that all of the points on that line are now included in our solution set. And let's say I was trying to solve a compound inequality. I can actually graph multiple inequalities on this grid to find overlapping solution regions. For example, I could add the inequality y is less than negative x minus 2. I can see that all of the points in this overlapping region would satisfy both inequalities. And not only does Desmos make it easy to visualize solutions to inequalities, but you can also use this shading technique along with sliders and restricting domains to design some incredible artwork. If we go back to the Desmos homepage, notice there's an option at the top here to see a gallery of artwork that is being submitted to Desmos. So if I click Gallery, I can scroll through some of these amazing submissions to see the power of Desmos. Like for example, if I click on these flags, I can see that Desmos can be used to graph flags of different countries from all over the world. Or here's a submission that has a picture of Earth with a slider that allows you to rotate the Earth. Or here's an amazing one that makes use of the 3D graphing calculator and allows you to use a slider to see the seasons change in this scene. And here's one more fun one that shows some line art and makes use of lots of different sliders. I'll speed it up so you can see what happens. Must know number 5, how to use Desmos for statistics. In Desmos, we can store data as a list using square brackets. For example, let's create a list of numbers representing the test scores for my first unit test in my calculus class. So I'll say A equals, and then in square brackets, I'm going to list all the test scores for the students in my class. And each test score has to be separated by a comma. And now that the list of test scores is typed, there are different calculations I can do to analyze that list. For example, I could find the average of those test scores by typing mean, and then in brackets, making its argument my list name, A. And that tells me the average test score was about 83%. I could also find the median test score by typing median of A, or the standard deviation of the test scores by typing stdev of A. And there are many other calculations we could do. To see a full list of them, so you don't have to remember all of these functions, just pop open the keyboard, click Functions, and you could scroll to the section on Statistics, and you can see all the different types of calculations that we could do. For example, I could use the count function for my list A, and it'll tell me that 24 students took that test. And now let's visualize this data. If I go back into the functions, I can scroll to the part about visualizations, and I see that there are 3 different graphs I could use to visualize my data. Let's start by making a box plot. So I could actually click this button box plot, or I could have typed it manually. And then I need to make a box plot for the list of data stored in function A, so box plot of A. Now, on the graph, I don't see the box plot, and that's because there were no test scores this low. The box plot is way over here somewhere. Instead of having to scroll all the way, if I go over to the equation editor, in the section where I typed box plot, I see in the bottom left, there's this zoom fit button. If I click that, it will adjust the scale of my x and y axes so I can very clearly see that box plot. And instead of a box plot, if I would rather a histogram, I'll X out this box plot and I'll get a histogram for my list stored in A. Now I can see in the equation editor, it tells me the arguments should be the data set A, comma, the bin width, which it's defaulting to 1. I think I'm going to make the bin width, I'm going to make it bigger. I'm going to make it 10. And then I'll want to zoom in so I can see all of these bars. So I'll hit this zoom and fit button in the bottom left. And there's the histogram of my test scores. So these were the statistical analysis tools that you can use when you have univariate data. But what if we have bivariate data? Let me clear all of this and recenter my grid. If we have bivariate data, we could visualize it with a scatter plot simply by creating a table of values for the data. So I can click this plus sign in the top left above the equation editor and choose table. And then I can enter some data into this table for whatever my variables x and y are. And notice as soon as I started entering the values, Desmos started plotting the points on the grid. And I'll click the zoom fit button so I can see all of the points clearly. And let me make the points a bit bigger by clicking the settings gear, clicking this red circle, and making the thickness from 8, let's change it to 15. And if we suspect a pattern in this data, we could perform a regression. For example, if I think this data follows a linear trend, I could regress it against a linear function. I could say y1 and then use a tilde sign to say approximately follows, and then I'll write a linear function. I'll say m of x1 plus b. And when I do that, notice it actually gives me the r and r squared values, and it gives me an option here, plot, to plot the residual values for each point. So notice the green dots are the residuals. They're values which were added to the table automatically by Desmos. Just tell me each point's distance above or below the line of best fit. But there may be a better regression model than this linear regression model. Let me get rid of it. But instead of having to type manually different functions to regress this data against, we can click beside the table this button here that says Add Regression. And then if I toggle this list, there are a bunch of different regression models I can scroll through. I could change it to a quadratic regression, which has a better r squared value, or even a cubic regression. I can see the r squared value is very high. So this is a great regression model for this data. Notice if I plot the residuals, their values are all very small. Must know number 6, probability tools. Desmos has built-in probability functions that allow us to simulate randomness, visualize probability distributions, and calculate probabilities. Whether you're working with discrete or continuous probability distributions, Desmos provides an intuitive way to explore these concepts. Let's start by looking at a binomial distribution. In Desmos, you can visualize the probability mass function for any binomial distribution by inputting binomial dist and then giving it 2 arguments, the number of trials and the probability of success. So let's create a binomial distribution for an experiment that has 10 trials and a probability of success of 0.3. To do that, I'll input binomial dist, 10 for number of trials, and 0.3 for the probability of success. I'll hit the zoom fit button, and there's my probability mass function. Let me give this distribution a name. I'll call this A, so A equals this binomial distribution so that I can reference it for doing calculations. To find the probability of having any number of successes in 10 trials, I can just look at this probability mass function. For example, the probability of having 2 successes in 10 trials, if I click on this point that has an x value of 2, I can see the probability of 2 successes is about 23%. Or I could type in the equation editor a.pdf of 2, and it gives me that same value of 23%. And if I wanted the probability of a range of successes happening, I could use the cumulative mass function or cumulative distribution function, CDF. For example, if I wanted the probability of having less than or equal to 6 successes in 10 trials, I could just type a.cdf 6. And there's almost a 99% chance of having less than or equal to 6 successes in 10 trials. Or let's say if I wanted the probability of between 4 and 6 successes, including 4 and 6, I could type a.cdf with 2 arguments, the lower and upper boundaries, 4 and 6. And that'd be a lot faster than adding 3 PDF calculations together, right? This would be the same as doing a.pdf of 4, 5, and 6 added together. Now let me get rid of all of this, and let's look at a continuous probability distribution. If I had a set of normally distributed data, let's say their IQ scores, with a mean of 100 and a standard deviation of 15, we can visualize its probability density function by typing normal, dist for normal distribution, and then inputting 2 arguments, the mean and standard deviation, 100, 15. And then hit the zoom fit button, and I'll name this function A so that I can reference it for calculations. The total area under this curve is 1, which means the area between 2 points represents the probability that a random person's IQ falls within that interval. So if I wanted to calculate the probability of a random person's IQ score being less than 90, I could calculate it by typing a.cdf of 90, and it'll give me about 25.2%. But I think a better way to calculate this is by checking this box underneath the normal distribution function that says find cumulative probability. If I do that, I can set the minimum and maximum value, so I'll set it from negative infinity up to 90, and then on the graph it actually shades that area for me. So I can see the area under the curve less than 90 is 0.25, 25%. And let's say I wanted to calculate the probability of a random person's IQ being between 120 and 140, I could type a.cdf of, give it 2 arguments, 120 and 140, the lower and upper boundaries, or I could just do that up here by changing the min value to 120 and the max value to 140. And that way I can actually see the shaded area on my graph. And now let me show you how we could set these upper and lower boundaries to variables to make this more of a dynamic visualization. I can change my min to A and my max to B, add sliders for them, and then change their min and max values. And then I can adjust these sliders to find the area between any two A and B values that are my min and my max values. And it might be useful to actually plot these points A and B, and then give them labels based on just their A and B values. If I click the label icons, it's going to label them as coordinates. But I just want point A labeled as 79, not 79, 0. And I want it to change dynamically with A. So what I can do, I can type $, and then inside curly brackets, A. That'll give it the label that is equal to the value of A. And I'll do the same thing for B. And now as I change A and B, those labels are going to change, and the area gets shaded in between the A and B values. And then maybe I actually want this area to be labeled somewhere. Well, let me create a function that calculates the area. So I'll say B equals A.CDF between A and B. That finds the area between A and B. And then I want to have a point that shows that value. So I'll make some random point somewhere on my graph. I'll make the point 50, 0.02. And I'll make its label. I want it to say area equals, and then the value of that B function that I created. So $, and then in curly brackets, B. And then if I wanted to, I could make this label bigger. And I'll uncheck the point so I don't actually see the dot, I just see the area label. And then as I change A and B, notice that it has this area calculation being recorded on the screen. And now one more cool thing I want to show you about probabilities is, let's say we want to generate a random IQ score from this set of data. I could type a.random and then open brackets, and it'll give me a random IQ score based on this set of normally distributed data. But let's say I wanted 3 random IQ scores, I could just change the argument to 3, and then it'll give me a list of 3 random IQ scores. Another useful random function, let me get rid of this one, is let's say I wanted to generate any random number within a given interval. If I type random and then open brackets, Desmos defaults to giving a random value between just 0 and 1. If I wanted 3 random values, once again, just change the argument to 3. Most of the time, you would want a random integer between a lower and upper boundary. To do that, we could type floor 100 times random, open brackets, and we'll just get one value for now, so I'll make the argument 1, plus 1. And now this function gives me one random integer between 1 and 100. If I wanted it between 1 and 200, just change that first value to 200. But I'll put it back to 100. And let's say I wanted to get 10 random numbers between 1 and 100. I'll just change the argument on random to 10. And now I have a list of 10 random numbers between 1 and 100. And we can make this list as big as we want. Must know number 7, the other calculators available in Desmos. Beyond its powerful graphing calculator, Desmos offers several other specialized calculators that can be incredibly useful for different areas of math. Let's take a quick look at them. There's the 4-function calculator, which is a simple and user-friendly tool designed for basic arithmetic operations, such as addition, subtraction, multiplication, and division. It's great for elementary math students or quick calculations without extra complexity. If I click on Math Tools up top here, I can see that there's also a scientific calculator. The scientific calculator is perfect for more advanced calculations, including exponents, square roots, trig functions, and logarithms. And then back into the math tools, the next one I want to show you is the matrix calculator. The matrix calculator is designed for working with matrices, making it useful for linear algebra and higher level math courses. I can create a matrix by just clicking this new matrix button and choosing how many rows and columns that matrix has. If I had a linear system of 3 equations in 3 variables, I could create an augmented matrix for it by inputting its values into matrix A that I have here in this calculator. And then I can press enter to input this matrix into its stored memory, and then I can put that matrix into reduced row echelon form by inputting an argument of A, and then the 4th column will give me the solution to this system of equations, 2, 3, 1. But also, if I clear all of this, we can do more simple calculations with matrices as well. I'll create 2 matrices, and then I could do lots of simple calculations with these, such as adding the matrices A plus B. I could multiply these matrices together, subtract them, or with one of the matrices, I could transpose it, or find its inverse, or I could find the determinant of matrix A. So these additional calculators ensure that Desmos isn't just for graphing. It's a tool for all levels of math, from basic arithmetic to advanced algebra and calculus. Must know number 8, the geometry tool. I'll open it here. And then I'm going to start by going into the graph settings, and I'm going to add a grid and axes and enlarge it. And I'm going to show you a bunch of the different functions available here for geometric shapes. And then I think a good way for me to show you what this tool is useful for is to do an example I do with one of my grade 10 math classes. Let's find the circumcenter of a triangle that has vertices at A, 2, 0, B, 2, 6, and C, 10, negative 2. But instead of typing it like I typed A and B, another option would be to use this toolbar at the top, click the point, and then go ahead and plot the point anywhere on the graph we want. So to plot at 10, negative 2, I might have to move over a little bit with my graph, click the point option, and then plot a point at 10, negative 2. Now it didn't show up in the equation editor, but if I click this little geometry button here, I'll notice that it did make this point. If I drag it down to the equation editor, I see that it named it point 1. And then I could give each of these points labels. I could label them based on their coordinates, or I could give them names based on the names of the points A, B, and C. And now if I open up this keyboard in the bottom left, if I click on functions and scroll down to the geometry section, I see there's a bunch of different geometry tools I can use and different measurements I can make in this geometry calculator. But instead of having to remember these functions and what arguments they take, it's often useful just to use the toolbar at the top here when constructing shapes or doing calculations with them. So for example, if I wanted to create the triangle by making the 3 line segments to make up this triangle, to create the line that goes from vertex A to vertex B, I could type segment A, B, or instead of having to type that, in the toolbar at the top, I could just click on this line segment option and then click the starting and end point A and B. And I can do that for all 3 sides of this triangle. And then I'll actually bring these 3 lines down into the equation editor. I said we're going to want the circumcenter of this triangle. That's the point where the right bisectors of these 3 sides intersect. So if I want the right bisectors, I'm going to need the midpoints of all 3 sides. So I could type midpoint of line 1, and it'll give me the midpoint of line 1. Or instead of having to type it, I could, up in this toolbar at the top, click on the point, click it again to drop down the menu, and then click midpoint. And then just click the line that I want the midpoint of. So I'll do it for all 3 of them, and notice the midpoints have been plotted for all 3 lines. I can drag down those 3 points so I can see what their labels are. And now I want the line perpendicular to each of those 3 sides going through those midpoints. So I can click this line segment, click it again to drop down the menu, and click perpendicular. And then click the line I want it to be perpendicular to, and then drag down to the point I want it to go through. So I'll do that for all 3 sides so that I have all of their right bisectors. And then the circumcenter is at the point where those right bisectors intersect. And I could label that point just by clicking the point option, and then clicking where the lines intersect. I'll drag that point down, so maybe I could change its settings by clicking the gear settings here, clicking on that intersection point, and I could make that point bigger and maybe change its color. And I'll label it with its coordinates by checking the label box. So the circumcenter is at the point 7, 3. And it's called the circumcenter because if I created a circle by clicking the circle tool, centered at that point 7, 3, I would notice that if I dragged it out, that circle would go through all 3 vertices of the triangle at the same time. That's why it's called the circumcenter of the triangle. And there are a couple other useful tools. Let me delete all of this except for the original 3 points. Instead of constructing the triangle by making all 3 line segments separately, I could choose this polygon option and then click on the 3 points that form this polygon. And then I should drag this polygon down so I can see its name so I can reference it for what I'm going to do next. I'm going to make this triangle bigger or smaller using the dilate function. So the dilated version, I have to give it a name. I'll say d equals dilate, and then it needs to take 3 arguments. The polygon that is going to be scaled up or down, so polygon 1, a point where I want the center of the polygon to be at, and then the scale factor. I'll call it a right now, and then add a slider for that, so that you can see this polygon getting bigger or smaller as I move the slider. And then another option, instead of dilating the polygon, I could rotate it. So I'll say d equals rotate polygon 1, comma, click the point about which I want to rotate it, so I'll do about the center of this triangle, and then comma, how many degrees do I want to rotate it? So I could rotate it 180 by typing 180, or I could once again use a slider. I'll put a variable a, and then add a slider for a. And then notice as I move the slider, it's going to rotate that shape. Must know number 9, the 3D graphing calculator. So let me click the 3D option. This is the most exciting new addition to Desmos. It allows us to visualize functions, surfaces, and vectors in 3-dimensional space. In this 3D calculator, we can plot equations in terms of x, y, and z, just like in 2D, but with an added depth dimension. For example, if I enter the equation z equals x squared plus y squared, it will generate a paraboloid, which is a curved surface extending upwards from the origin. And I can rotate around this, and I could zoom in on this so that I can better understand the properties of this function. And I'll clear this and show you another thing we could do is to graph systems of planes and explore their intersections. So for example, if I graph a standard form equation with 3 variables, it will graph the plane defined by that equation. And if I write the equation of a couple more planes, I could rotate this graph around and see from different perspectives how these planes intersect. And I could see these 3 planes intersect at a single point. And clearing these, I'll show you one more thing with the 3D graphing calculator, and it's how to graph vectors. We'd have to start by plotting different points in 3 space. So I could plot a point at point A by saying A equals, and then write its x, y, and z coordinates. So let's say 1, 2, and 3. Notice it's able to plot that point that has an x and y coordinate of 1 and 2, but it also has that z coordinate, the added depth of 3. And then I'll plot another point, point B, and then I can create a vector that connects those 2 points by writing vector, and then the starting point and end point, A, comma, B. And then it draws the vector connecting those points. And then if I had one more point, let's call it point C, I could create another vector that goes, instead of from A to B, let's make it go from A to C. And then I'll give those 2 vector names. I'll call them vectors U and V. I could do calculations with those 2 vectors. I could do U plus V, and it'll graph the sum of those vectors, or U minus V. Or if I choose the multiplication operation between those 2 vectors, it's going to do the dot product of the 2 vectors. If I wanted the cross product, I would actually have to type the word cross. And then it gives me the vector perpendicular to both vectors U and V. Must know number 10. The teacher tools available in Desmos. If I scroll down on the home page, I can go to the teacher home. There's lots of amazing pre-made resources you can use, or you could even create your own activities. But what I like to do, I like to scroll through, go to the featured collections, and then I can look based on grade level or based on topic, what pre-made activities I could use with my students. So if I go to, let's say, Algebra 2, I can see a bunch of activities suitable for Algebra 2. And one of my favorite activities are these marble slides. And if I click on an activity, and what I can do here is I can actually preview this activity. I notice there are 24 cards in this activity. In each of these cards, they're going to be launching marbles and trying to collect stars. I can go through each of the different cards in this activity and see what the students are going to have to do. Like for example here, if I launch the marbles, it's not going to collect all the stars, but it says to change the equation of that exponential function to collect them all. So I think if I just horizontally reflect this exponential function, it should be able to collect those stars. And then if I like this activity, there's a couple things I can do. I can click this plus sign and add it to one of my own personal collections, or I can assign it to my class. I can assign it to a class that I've already pre-made, or I could just create a single session code. That way students don't have to create accounts. Now I won't be able to track their data as in detail as I would be able to if they were in my class, but this makes it a lot faster to get students actually engaged in doing the activity. And going back to Desmos Classroom and back to featured collections, if I scroll way down to the bottom, I want to show you one of my other favorite activities to do with students. This one's called escape rooms. There's 2 different escape rooms that students can try. And if you preview them, you can see that they're actually really fun to do. You can go through in these rooms and try and figure out how you can escape the house. Like finding the ice cube, collecting it, seeing that there might be a key inside these ice cubes, so taking it over to the water, melting the ice cube, and having a key. And then eventually you'll discover that there's this hidden room under the couch. You can use the key to get downstairs. And then there are so many different rooms in this escape room, and students will have to play around and use their problem-solving skills to actually get out of this house. So I would highly recommend looking through all of these different featured pre-made activities. There's lots of different great ones that'll be great for your classes. And going back to Desmos Classroom, there's one more thing I want to show you. There's this new thing called polypad manipulatives that also might be useful to you. I'll launch the polypad, and then I see there's a ton of cool tools in here. Lots of things we can do with numbers, fractions, algebra, probability, lots of cool things. Let me just show you a really simple example so you can see how this works. Let's say you're just working on adding numbers. If I was just adding 17 and 16, I could type that equation, and then I could represent each of those numbers with number tiles if I wanted to. If I have 17, that's a 10 and 7 ones, and 16 as well. Or I could do it with number cards if I wanted to. And then I could show that when adding them together, I can take my 17 and then add the 16. I could take 3 of the ones from the 16, add them to the 17, and then I have another group of 10. And then combining these together, I see that I have 33 as my answer. Or with the number cards, I can split each of those number cards, and then combining these together, I see that the 7 and the 6 make 13, which I could split into a 10 and a 3. So I have 3 10s and a 3, making, if I merge them together, 33. So lots of different ways to show why this is 33. And if you want to test out if you're right, you could even in this algebra section, choose this balance scale, and then put the question on one side and what we think the answer is on the other side and show that it's perfectly balanced. So I hope this video has inspired both students learning math and teachers teaching math to make the most of Desmos. Whether you're solving equations, analyzing data, or exploring probability, Desmos brings mathematics to life in a way that makes learning more engaging and meaningful. Jensen!